So now let's talk about stable and unstable systems. That is, how do you tell if a system is stable or not? So in fact, that's what we like to do, is determine whether a system is stable or not. So a system is bounded input, bounded output stable, or BIBO stable, or BIBO stable, depends on how you want to pronounce it. If basically the input is bounded, so if a magnitude of x of t, or magnitude of x of n, if it's less than or equal to b, so there should be another equal here, then there's a function f, which is finite, so f of b is finite, and basically the magnitude of the output is bounded by f of b. So if the input is bounded for all time, then the output is bounded for all time. That's the definition of stability. So to show a system is stable, you basically have to find the function f of b. So if we have yn is magnitude of x of n squared, then if magnitude of x of n is bounded, then the output is also bounded by b squared. So here f of b is b squared, and we're done. We can show that the instantaneous power system, the system that calculates the instantaneous power, is in fact stable. What about the integrator? So we suppose y of t is this integrator which goes from tau equals minus infinity to t of x of tau d tau. Now if we pick x of t is equal to the unit step function, that's bounded for all time, it's bounded by 1. Then we get the ramp function, and the ramp function goes off to infinity even though x of t is bounded. So that system is unstable. What about a more complicated example? So suppose we have y of t is the integral from 0 to t of x of tau, but tau times tau to the fourth, e to the minus 2 tau, cosine 3 pi tau d tau. So that's very complicated. We have to, what kind of weird system is this? So when you want to answer whether the system is stable, you have to really start with a guess. And so let's guess that it's stable, and then we can walk through the logic of how to show that it's stable once we guess that it's stable. So we have to show a bound on it. So suppose x of t is bounded by b, right? Then if we take the magnitude of y of t, then what we want to do is develop a sequence of upper bounds on the magnitude of y of t, plug in our x of t, and show that this upper bound is still finite. Okay, so let's look at this. We can take the magnitude of y of t, which is the magnitude of this whole integral and all the junk inside. Then we can upper bound that by moving the magnitude inside the integral, and then the magnitude of a product of things is the product of the magnitudes, so we get the product of the magnitude of x of t, tau to the fourth, e to the minus 2 tau, and cosine 3 pi tau d tau, magnitude of all of those. Now we know that the magnitude of x of t is bounded. So this term here, we can replace this by b, we can get an upper bound by b, and this cosine is always less than 1, so we can upper bound this by 1. So that leaves these two terms here. So the question is, what happens to those two terms? Well, now we're left with y of t is upper bounded by b times the magnitude, the integral of the magnitude of t to the tau to the fourth plus e to the minus 2 tau d tau. So what happens to this? So the thing to look at is that the exponential decay is much faster than the polynomial term. So that is, this exponential is going to kill this tau to the fourth as time goes to infinity. So in particular, we can say that there's a time capital T such that for t greater than capital T, we know that this whole term is actually less than e to the minus tau, which is, it decays a little slower than e to the minus 2 tau, and so we're being a little sloppy in the bound here. But basically we're saying eventually e to the minus 2 tau kills the tau to the fourth. And so for t less than capital T, the quantity here, this quantity here, e to the minus 2 tau is always less than 1. So it's less than t to the fourth. So the whole thing gets bounded as b times t to the fifth, I guess, because we're integrating this t to the fourth, plus the integral of the second half for t greater than t, so from capital T to t of e to the minus tau d tau. This thing is bounded by 1, so we get this total bound b times t to the fifth plus 1. So that was a little bit messy, but basically, you're just trying to show that there is some upper bound which is just a function of b. So here in this case it's b times some constant, which is maybe pretty big. But regardless, it's bounded, which means that this system is in fact stable. So what happens if you guess wrong? Well, then you would not be able to do this process. I mean, that doesn't give you much hope. But if you try doing this process where you upper bound y of t with this magnitude and start peeling off terms as you can, you should see it basically not working out at some point if the system is in fact unstable. So then you have to go back and change your guess. So what if you do that, and what happens then? Well, let's look at a simpler system if we want to show a system is unstable. So let's look at the system y of t, which is e to the t times e to the tau times e to the t minus tau d tau. So I'm going to guess actually that this system is unstable since e to the tau is blowing up. So what you have to do when you suspect a system is unstable is you have to find an input. Usually it's a pretty simple input. You can find an input such that the output blows up and the input is still bounded. So here in this case we can just plug in the unit step function and you can see that this integral is going to diverge. Another example is our modulator system, so x of tau cosine 6000 pi tau d tau. So what if we integrated the output of the modulator? Here I can't stick in x of t is equal to u of t, but if you let x of tau here be cosine 6000 pi tau, so x of t is 6000 pi t, then you get the integral of the cosine squared, and that integral is going to diverge as t goes to infinity. So we can see that that system is also going to blow up. So both of these systems are unstable. So as an exercise for yourself, you should try to figure out if each of these systems is stable or unstable. And remember, to show that a system is stable, you have to say, suppose I have a bounded input, then show the output is bounded. And to show that it's unstable, you should try to find an input which is bounded, which causes the output to blow up in some way.